Hi everyone, I want to talk about the recycling of lithium batteries today. So, if you're curious why I'm deciding to do this lecture, my professor today talked about lithium batteries and she brought up the point of problems in recycling of these batteries. And that made me wonder, what has been done, what is the industry standard, and why aren't we seeing the recycling of these batteries be a commonplace? And we'll speculate why it would be a really good idea and why, in fact, it's not being done. And we're also going to explain what industry is doing. Okay, so a typical lithium battery follows this simple cell layout. You have this anode here, which is graphene, or sorry, graphite, and it's these layers of cyclic carbon sheets, and in between you have these lithium ions. So that's a lithium. It's actually not lithium plus. Sorry, it's just lithium. But then what's going to happen is it oxidizes to lithium plus, and you release electrons. And the electrons are going to flow from the anode through your circuit to do some sort of work, and then it ends up at the cathode. And in the cathode, it's this layer of typically cobalt and oxygen, and this rich layer allows the acceptance of lithium ions as they permeate through the electrolyte, and they become part of the cathode. And you'll find the E cell to be about 3 volts, so pretty good E cell there. Remember, delta G equals negative N F, and then E cell, whatever that E cell is. And since it's positive, right? Faraday's constant positive, N is positive. We're going to expect delta G to be negative, and that's good because we want a battery to be spontaneous. You're also able to charge this battery too if you allow electron flow into the anode. Okay, so now that you understand kind of how this battery works, let's describe some issues. And the most important issue is the materials used to make them. Now, what this chart is saying is it's showing you all the elements by their atomic number on the x-axis, but on the y-axis, we show the abundance relative to a million silicon atoms. So we kind of set the baseline here at silicon, and we say, okay, relative to that, what is the Earth made of? Well, what's used in these lithium batteries, of course, is, well, lithium, which is relatively abundant, about 10 to the 3 less, right? If we look at this gap here. But also what's used are some rare metals like cobalt, for example. Cobalt's a really common one. If we go back here, it turns out that when your lithium migrates to the cathode, this lithium ion is going to bind with a cobalt dioxide. I'm not sure that's how you would say that. Cobalt 4 oxide, and you get your species with the migrated lithium. Okay, so cobalt's a very important component to this battery, and compared to silicon, it's about, and we know the mantle is made of silicon, so really abundant stuff. We know cobalt, though, is only about, well, I would say it's about 10 to the 2, right? Or probably not even less than that, just 10 compared to a million. So if I had a bag of a million atoms, right, only 10 of them would be cobalt, which is not good. And it's the reason why these lithium batteries can be so expensive is because we're using these really rare earth metals. Okay, so this whole PowerPoint, I didn't want to die on that hill too much, but this is the recycling processes that we see, the research and the industry practices that resulted from the research has shown this very basic kind of lifeline. So without recycling, well, we mine, right? We mine the cobalt, we mine the lithium, we mine everything that we need. We refine ores, right? That costs some economic input. We create the cathode and the anode, of course. You need the graphite for that as well. But the cathodes are the more rigorous thing to make, I would say. You manufacture the battery, so you encase everything, and you build the battery. You use it, okay. So you're going to use the battery, and unfortunately, what we're seeing a lot of is this battery, when it goes dead, goes straight to a landfill. Because sometimes it's just easier to start at the beginning and start from the mining and go back to the battery use. But this isn't really renewable. Notice that we're not really looping back if we go from landfill to mining. However, what we can do is we can do these types of recycling. And one way that we're not going to talk about today is direct recycling. That's very simple. You just if conditions aren't too bad, you might be able to regenerate the cathode or regenerate something in the battery that went wrong, and you can go right back to building back your battery and then using it again. So that's a good method. It's the most viable because it's not the most rigorous. But what if you have just a completely shot battery? Well, what we're going to see later is you get this, they call it a black mass. And basically that's just a lump of crude dead battery mass that's a result of rapid use. You charge the battery, it dies. You charge the battery, it dies. It charges the battery, it builds this black mass. And we can do two sorts of processes, and typically I'll add a little bit. We have hydrometallurgy and we have pyrometallurgy. It's just processes of extracting metals from a crude compound. That's what metallurgy means, extracting the metals from it. And typically what we're going to look at in this video is the pyrometallurgy route. But what we'll see is older methods may have just went directly pyrometallurgy, but in these aqueous in recent industrial methods, they started to hybridize, where then they converge to the hydrometallurgy, right, to get refining, and then they'll go right back to producing the cathode. And we're going to see exactly how this process works. It's the most rigorous. In my opinion, it's probably the best way to go about things, right? If you just do this direct recycling, you're probably not going to get the best performance, whereas hydrometallurgy hybrid processing of recycling, you're getting a little bit better. You're getting basically a fresh start. You're starting from square one, but you're not taking more minerals from the ground, so it's renewable. Okay, so let's talk about the process that goes on in these metallurgy processes. So pyrometallurgy and hydrometallurgy. This is just a generic thing. We'll get into the details in a second. But you have a dead battery, and you use mechanical force to break it apart, of course, right? You have this battery, you break it up into its metal, its plastic, its gunk, its electrolytes, that stuff. And that's fine. Typically, you might see this with a mill, right? Or I believe they call it what's it called there? I shouldn't say. So I forget what it's called, but they have a process that they call this, and it is going to completely rip this battery apart into its fundamental components. You'll output a lot of things: the metal, plastic casings, electrodes like the aluminum or copper that we put in the ends. But you'll also find this black mass, and I alluded to this earlier, but this is really important. This mass here is consisting of copper, or sorry, not copper, cobalt. You'll have some iron in there depending on the battery. And you'll have your lithium in there too, but it's wrapped up in this matrix, and this matrix is really complex. There's graphene in there, right? Or sorry, graphite. I always mix up the two. right? So you'll have some graphite in there, and you'll have some other junk that you don't know about, right? You also have a little bit of electrolytes still in there, volatile compounds as well. Just a big mess of a matrix. So yeah, anode and cathode materials is what makes this black mass up. So what this process is going to do is extract those metals. So a pretty important process. Okay, so I found this image online, and I think it's the best way to show the industrial process. And I apologize that it's a little blurry. I didn't expect for it to be this blurry, but it is. Basically, you take this battery and you're going to treat it. You're going to basically do what we said back here and mechanically break it apart. And then you feed what's it called, the black mass into this hopper. So black mass goes in. So let me write that, black mass, which again is those metals that are inside of a pretty crazy matrix. Now you're gonna introduce this into this system here, this big column like furnace, and this zone is where pyrometallurgy is happening. So pretty obvious what this means. Pyro meaning heat or fire or just a lot of energy or heat being put into the system. Metallurgy meaning to extract a metal from. Sorry, I know my handwriting isn't the best, and this is quite a complex word for my pea-sized brain, but pyrometallurgy is happening here. We're going to find that everything after this is hydrometallurgy. But anywho, in the preheating zone, and we'll get to this, I'm just going to go through it really quick. In the preheating zone, we are just simply heating things up gently. All right. And what you're going to notice is you're going to have a lot of your gases and your solvents leave. And one of those gases that we'll find is lithium carbonate, and other sorts of lithium-based aerosols that are going to evaporate. And the lithium, using these fancy filters, gets sent down into this formation of hydrometallurgy. But then any other gases like CO2 or anything are going to go through this this output gas column or chimney, you should say. So yeah, it goes through this line and out. Okay, so we're successfully trapping the lithium. So from the rest of the compounds, we get rid of the gas. We selectively, using this selective filter, take the lithium, although it's not completely pure, so we do this hydrometallurgy to it afterwards, which we'll get into later. But then what's going to happen is after this preheating zone, right, the black powder continues to go down into this pyrolysis smelting kind of zone. In the pyrolysis zone, the matrix is getting ripped apart, and what you're going to get is you're going to get some highly oxidized species that are not metals, which are going to drip into this slag pot. But your your metals like cobalt and iron are going to get stuck in this alloy ladle, and it just collects it. And then these alloys, the metals, are going to then undergo hydrometallurgy, which again we'll get into. But it should be interesting to understand why they're separating. It's kind of like if you've ever done, in organic chemistry, when you do phase separations, right? Organic and aqueous phase separations, right? What you do is the less dense material rises to the top, where the heavier materials sink to the bottom. And in fact, cobalt and iron are the most heavy, so they're going to sink to the bottom of the furnace in the smelting zone, where the slag, which is all of that matrix gook, it's just stuff that we don't really care about, it's a little less dense than metal, so it's going to rise. It's usually oxide rich, so again, not very dense. It's going to rise, and then it's going to be outputted into the slag pot. And that's how we're doing sort of like a chromatography almost. I mean, not really chromatography, but like pseudo chromatography on these alloys. But inevitably, in your alloy ladle, you're going to get things that really are not metal. You might get some residual slag-like material that's coming through. So we're going to go into these ideas of hydrometallurgy, both for the lithium parts and the cobalt and iron parts, where we go through an acid leaching reaction, which we'll get into the specifics of how those reactions work. But then you'll also see in this oxidation tank, and you're gonna get oxidation of your metals. You're going to form metal oxides, and then up here we have a precipitation tank. We're trying to make lithium carbonate, and we're going to combine the two, right? The lithium carbonate and your iron oxides. They're going to react in this sintering furnace, and you're going to output the cathode. So you're going to get that lithium cobalt oxide compound that is desired. Remember, if we go back, that is the cathode that we're looking for. We can charge this, separate the lithium, and get a good working battery again. So hopefully you see the benefit there. And this whole process is mediating that. I hope you find this really cool. So remember this heating column, that's pyrometallurgy, and this section is this is hydrometallurgy all in here. So I've kind of decimated the slides. Allow me now to walk you through in a little more detail, just kind of recapping each section, looking at each important section. So in the preheating zone, remember, we're going to collect a lithium vapor up here and desolvatize the mass that's going to enter the pyrolysis zone. But remember that we're also going to get that output of unwanted gas, right? So when we heat a sample, it might give off some gas. That's not good to have in a furnace. That's added pressure. We don't really want that. That can also affect some of the smelting that we get. Importantly, the electrolyte and the H2O will be off-gassed. Okay, and then like I said, lithium-based gases are going to get trapped by this filter here. Okay, so remember in the pyrolysis zone, I said that the less dense materials will rise. That's the slag. That's everything that's really not what we want, right? The matrix, where we're kind of getting rid of that matrix, and the alloys drop down into the ladle. Okay, and then we're going to talk about the hydrometallurgy. So let's consider for our discussion here an alloy going through the hydrometallurgy section. So in the leaching tank, we could expect a reaction kind of like this. So if you have cobalt, right? So you have a crude cobalt solid, and you react it in this acid tank, right? It's at about 55 degrees Celsius or a little bit higher than that. And you react it with H2SO4, you're going to get a metal salt that looks like this. So you'll get cobalt sulfate. And you'll also get hydrogen gas. All right, so in this reaction, you're gonna, and don't really worry about the hydrogen gas, is not important, but this cobalt sulfate is very important. So input, you get the cobalt, right? The cobalt's fine. It's just let's now convert it so that we can sinter it into lithium cobalt oxide, the cathode that we want. So to do this, we kind of prepare it by making sure that the cobalt isn't really attached to anything, right? Some of that cobalt might be wrapped up in some sort of reaction. Now we know that this may dissociate, so in the next reaction, the oxidation tank, we can expect cobalt to take the form of cobalt hydroxide. So something like this, cobalt hydroxide. And when we react it with oxygen, okay, I'm not going to use any, or I guess I should keep it stoichiometric, or balanced, I should say. When we react it with 1/2 oxygen for every 3 cobalt hydroxides, we're going to get cobalt. There's 3 of them, and then 4 oxygens in the solid. And then we get 3H2O. So hopefully you can see we went from a salt to an oxide, and that's getting us one step closer to that lithium cobalt oxide cathode that we really want to get at the end. And these are the reactions. So this is happening in the leaching tank, and this reaction down here is happening in the oxidation tank. So an important fun reaction. The precipitation reaction is really easy. You'll have lithium hydroxide, and then you would react it with some sort of carbonic acid, I would guess, or carbonate, and that would precipitate lithium carbonate because carbonates aren't really soluble. So I won't show that reaction very much, but important to know. Okay, and the final reaction is going to form our cathode. So you keep this the sintering furnace at 900 degrees Celsius, right? That's industry standard. If we take lithium carbonate and we react it with cobalt like so, we're going to form our lithium cobalt oxide compound that we want. So hopefully you can see how this recycling process, this is a hybrid between pyrometallurgy and hydrometallurgy. It's a very important process for the recycling of these batteries. And you might look at this and you're like, well, why isn't a lot of people using this? In fact, in America and Europe, there's a lot of these plants out there. But, well, actually, there's not a lot of these plants out here, I should say. Compared to the amount of mining and production, it doesn't really match with the amount of recycling we're doing. And the reason for anything is this beautiful thing we call money, right? Money is the driving force of life, and it's just a sad reality we live in that money controls all of us. But in fact, the reason that we don't do a lot of lithium battery recycling is money. So I have a little bit of statistics here. It is expensive, okay? The plants need to avoid the safety risks. If you remember, lithium is pyrophoric. So when you're working with lithium, when you're working with these extremely dangerous conditions to react all this black mass, and it's really an intense reaction chamber system, and you need really high levels of equipment to do this. And not to mention, you're keeping a furnace. If we go back, you're keeping a furnace upwards of 1400 degrees Celsius, almost 1500 degrees Celsius. That's really expensive. That's a high energy input. And that's where the economic return comes into. When we look at the profit margins between when we directly mine these materials and make the batteries versus when they're recycled, we're going to see an 88% profit margin when we're mining these things. But when we recycle them, it drops to a substantially low 19%. So research that needs to be done. You can look into other kinds of battery types. Maybe switching up to like something like sodium migrating ions. That's research that's being done. And sorry, I want to point out one more thing. Only 5% of lithium batteries are recycled. So if you had 100 batteries and you use them, 95 of them are going to be going straight to the landfill, which is not good. That's polluting our environment. It's not a great process. Now, granted, is it that big of a deal? In the grand scheme of the Earth, probably not, right? Because all that matter is going to get, with time, sunk down back into the Earth, back through the crust into the mantle, to be moltenized, and it's literally probably going to do exactly what we're trying to do here as humans, where we're going to smelt it down, and it's going to go through all those processes again. But for the human race, it's not good because we're taking all the lithium out of the ground, and then that is big sad face. Okay, so I don't know if I have much more to say here. Hopefully you got to learn something about the recycling process. Hopefully you got to learn why we're not doing it. It's a really sad thing. And I want to make one more thing really clear. Research should be done, and I saw papers. I didn't look at them uh, very much, but some sorts of what's it called, of processes are just completely getting rid of pyrometallurgy to cut down on costs, and then they're just doing hydrometallurgy. And granted, you have to do more complex processes and more complex chemistry, such that the prices kind of balance out. But maybe one day we'll find a process that is going to bump up the profit margin. And I think that if our politicians were to maybe push maybe like a tax break, or sorry, not a tax break, a tax credit, right? Kind of like we saw with the IRA bill in 2024. No, 2020. I think the IRA bill came out. Well, it's been cut now, but just giving tax credits to incentivize companies to do this kind of recycling, right? Maybe they'll take a cut on their profit margin, but if you give them a good enough tax credit, it might incentivize it, or just some sort of incentive, or invest in research. Something where we don't see a lot of right now. Okay, I hope you guys enjoyed. Here are my sources. I pulled from them for all information that you saw today, all figures, and all talking points. So I hope that you guys enjoyed this video. If you did, please drop a like, comment, and subscribe. But I hope that you have a wonderful day. Bye-bye.